Okay, thank you so much. So as Eli said, the title of my study is High Executive Demand Elicits Increased Activity in Distributed Cortical Networks During Working Memory Performance. And so that sounds like a bit of a mouthful, but the premise of this study is we're basically looking at the neural underpinnings of a specific cognitive process that we're interested in looking at, and that's being called the central executive, and I'm going to get more into what that means in a few slides here. But we're going to start off with a few key terms and definitions here. So working memory refers to a cognitive system that is involved in the temporary storage and manipulation of information for the purpose of completing task-specific goals, right? And a palatable example of working memory is Susan trying to learn a new phone number. So that being 716-645-2222. So that's a UVPD phone number. Okay, and the ultimate goal at the end is for her to put it into her contacts. Down below is a schematic diagram of what working memory looks like. So initially, one of Susan's friends tells her about, the important phone number. That gets processed into her brain, and it gets put into working memory. So either Susan is going to constantly rehearse that number by repeating it, so 716-645-2222, and then eventually being able to put it into her contacts, or that information is going to get lost as a result of her not rehearsing it enough. And so as I said before, working memory refers to a cognitive system. So one of the core components of this system is something called the central executive. Right? And so this is one of 4 components of the working memory system, and it enables intentional control towards goal-directed behaviors and ignores extraneous stimuli. And what that basically means is, in this example here, Susan has a goal of finishing a Harry Potter book by the end of the week. And so she's reading, but her sister comes in and she starts watching TV in the same room, right? And what happens here is Susan now has to make a decision in terms of what she wants to focus on. So is Susan's central executive going to tune into the voices that she hears on the TV, or is she going to continue reading the Harry Potter book to see who gets into Gryffindor? And obviously, because her goal is to finish that book, she's going to finish reading that book and ignore the TV. Okay? And so we have 2 specific aims of this study. The first of which being, we wanted to identify brain activity patterns associated with increased recruitment of the central executive during a demanding task. And basically what that means is we're looking at what specific brain areas are particularly active when participants are forced to use the central executive in a task that which demands the central executive. And our second aim is we wanted to determine if a correlation exists between brain activation of the central executive and performance on tests of other cognitive domains. And just to break that down, so in other words, are brain areas associated with the central executive also involved in other cognitive abilities? Okay. So we have the cognitive process that we want to study, and we have our goals, but how exactly are we going to accomplish this? Well, what we wanted to do is we wanted to use something called electron encephalography, also called EEG. This is a type of brain scan where we're basically looking at action potentials within the brain, right? And the benefit to using this, among other options, is that it measures brain activity in a matter of milliseconds, right? Which leads to higher temporal resolution. And all that's trying to say is, if it measures brain activity in a matter of, so it measures brain activity in real time, which is really important for us to have, because when you think about it, cognitive processes happen in a matter of milliseconds. And so we really need a brain scan measure that's able to keep up with it. So what does EEG measure exactly? So as I said before, as I briefly alluded to, it measures event-related potentials. This is also abbreviated as ERPs, okay? And what happens here is they are small voltage changes generated from brain structures in response to specific stimuli or events, right? And so if you look down here as an example, we have a participant here and they're doing some cognitive task. So what happens here is we have a specific stimuli that shows up and the participant reacts to it and the brain reacts to it via event-related potentials, or the small voltage changes. And what you'll notice here is this weird-looking net. That is called an EEG scalp cap, and that has a bunch of electrodes pointed down towards the brain, which are supposed to measure and record the event-related potentials that occur in the testing environment. Okay? And what we ultimately get from that is raw EEG data. And then eventually we put it through an ERP averaging pipeline until we get presentable ERP data. So what you'll notice here is we have the stimulus onset here from the cognitive task the participant did, and then we have subsequent brain activity as a result. Now, if you can direct your attention to the P1, the N2, and the P3, what those represent are various stages of information processing that your brain naturally undergoes. Okay? Another thing I wanted to keep in mind is in the present study, the participants are doing exactly this. And what they're doing exactly in this specific study is a battery of cognitive tests. And I'll get to two that generated the most significant results. So the first of which is called the letter 3 back task. And this one is the most important because it probes at specifically the central executive, where participants have to respond to stimuli that was presented from 3 trials ago. And we have 3 trial subtypes, the first of which match, non-match, and lure. Okay? And if I can direct your attention to the top line of letters there, a match trial is when the current letter that is being presented to you matches with the letter that was presented from 3 trials ago. Okay? And the current letter that's being presented to you does not match with the letter that was matched from 3 trials ago. That is considered a non-match trial. And if you look at the bottom row, a lure trial is when the current letter that is being presented to you matches with the letter that was presented from 2 trials ago. But that's the thing. The test itself is trying to trick the participant and saying, yes, that is a match, a trial sooner than they should. Right? And we're particularly interested in how participants are going to respond to the lure trial because it's trying to trick the participants into thinking that, oh yes, this is a match. And it places a particularly high demand on the central executive. Okay, and remember, all this is associated with AIM-1. Now the letter series task, which is more associated with AIM-2, what this does is has an arrangement of letters from the English alphabet that had to be completed by the participant based on specific predetermined rules or patterns. So what you'll notice here is we have a pattern of letters here. So we have 1A, 2B, 3C, and 3D. And the participant has to respond with a single letter, right? And so the answer in this case is going to be D because we have 1A, 2B, 3C, and now 4D. Okay? And the last bit of ERP data analysis is something called source localization, right? And this I'll actually, not to get ahead of myself, but here. So based on EEG recordings resulting in ERPs, where in the brain is activity originating from? And what we did here is we took an S-Loretto approach within source localization, which is a method of estimating exactly, a mathematical estimation of where brain activity is originating from. Right, and so we get 3 crucial details from this approach. We get timing and magnitude of brain activity, but most importantly, we can see where it is located. Okay, so here again, we have our presentable ERP data, and then we put it through source localization, and we have what's called a flat map of the brain. So it might be a little hard to see, but this is the left hemisphere of the brain, and this is the right hemisphere of the brain. And basically what this shows is the more yellow a given area is, that signifies a high intensity of activation at a specific time point of information processing within the brain. So if you'll notice, this is P1 here. This corresponds to P1 on the ERP graph here. And by the way, this is all associated with the letter 3 back task. Okay? And so for the actual results itself, this is for the letter 3 back task, and this can be a lot to look at. But basically what we did here was once we got all the brain areas that were active in all 3 trials, what we did is we compared them to each other, right? So we had a lure versus match, lure versus non-match, and a match versus non-match trial contrast, right? The third of which you don't see here because that didn't generate any significant results. But what we're left here are 2 graphs here. And basically what we want to find out is, okay, so we have two trials here that we're comparing. Which of the two are most significant, right? And before I go any further on our findings here, I do want to break down this graph a little bit. So this is a piece of the lure versus match trial contrast graph. So over on the left here, you'll see we have our brain areas. They're in the left frontal hemisphere. And above here, we have our time, which goes by milliseconds, so 50 millisecond increments. And what you'll notice here is we have a color spectrum of darker orange, yellow, and white, right? And what these colors will correspond to is a specific brain area. So darker orange signifies that that brain area was specifically active in the lure trial. So it's basically saying it's strongly active in the lure trial at a given time. If you see yellow, that corresponds to a specific brain area at a given time. That means that that brain area was only slightly active during the lure trial. And if you see white, that means that there was hardly any activation of that brain area in the lure trial. Okay? So going back here, it's very clear here that the lure trial in both instances had more brain areas that were active, given just like the pure orange and yellow color that you see here. But we want to get a little bit more specific here. So what we found was more frontal areas, more occipital temporal, and more limbic area activation during the lure trial, right? And something to note here that we usually find these darker orange colors usually 300 to 500 seconds after the stimulus had initially been presented in the letter 3 back task. Okay? And the last bit of our results was when we were comparing the letter series task to each of the 3 trials within the letter 3 back task. And what we ultimately found here is we found a correlation between the letter series task and the letter 3 back task. Specifically, we found that there was a distributed network of activity in both the frontal and parietal areas in both tests. Okay? And our conclusions here is just a reinstatement of our purpose. So we wanted to identify brain activity patterns associated with increased recruitment of the central executive. And ultimately what we found is that the lure trials were significantly more active, had more significantly active brain areas than the other 2 trials, specifically the frontal, the parietal, and occipital and limbic areas. We also found that most of these brain areas were active at 300 to 500 milliseconds after the stimulus, and then we found that the bilateral, orbital, rectal, lingual, fusiform, posterior cingulate, and uncus, and the parahippocampal gyrus were the most active brain areas in the lure trial. And lastly, we wanted to determine if a correlation exists between brain activation of the central executive and performance on tests of other cognitive domains. And what we found was that the letter series task and the letter 3 back task shared frontal and parietal activation in both of the cognitive tests. Okay, and that's it. I just wanted to quickly give a shout out to the Climb Up Summer Program, grant funding from the National Multiple Sclerosis Society, Dr. Thomas Covey that is currently joining us, and the Division of Cognitive and Behavioral Neuroscience.